Good morning, everyone, and welcome to this tutorial for hacking HiC, where we'll be going through, for starters, we're going to go through the last homework exercise, the server that you had to exploit, and I will be walking you through that exercise. Then we will be doing exam Q&A, and lastly, we will be I will show you around the exam exercises that will appear on the Acme website very soon. So if you have questions, I think you hopefully have thought about what questions you want to ask before. We will get to those, but first we're going to start with the buffer overflow exercise. So you obviously you got this big heap of text. I gave you a little bit of sample code, and there was all of this explanation here. But I'm gonna just go to the sample code that I have, and this is just this exact same tarball that I gave you, and you see that this is still an empty script. So for starters, we need to change the URLs at the bottom of this script, because it was made last year, this script, and I forgot to update this for this exercise. So you should have changed this part to the proper website, and this part to the port 12345 that you had gotten. However, because the assignment has just disappeared from your website, and I'm running this locally, I will need to change this to localhost and that port. Okay, so you got this script, and you saw that it prints a whole bunch of A's if you just give it an argument, and you would see that this sort of thing would happen. Let's start, however, with just directly connecting, like was suggested on the bottom of the page. This is a program where if you give it some input, it will give it back to us. Sometimes this type of program is called an echo server, because all it does is echo, 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 etc. This in itself is not so interesting, so what you could have done to start with is just start figuring out what the limits are on this thing. And this still seems to work. So I just give it a whole lot of input, and you'll see what happens. So I gave it way too many A's, and you see here that it didn't output all of them. And you might even have seen that it produced some question marks here at the end as garbage. You also see that I even got kicked out of it. The program has apparently crashed because it was not giving me new input anymore. Those A's that I was typing myself, that were not returned back to me by the program. So clearly it crashes. So let me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I hope I've counted those correctly. Seems so. Let me copy those. 40, 50, 60, 70, 80, 90, 100. Still seems fine. Yep. Let me copy the whole 100. 101, 2, 3, 4, oh, something interesting has just happened. You see that up until 104, it kept returning exactly my input. But when I gave it 105, you see here that there's here 1A more than there is on this line. So something happened. This was also probably the time when you would see question marks disappear. That was because the program is actually getting some garbage as output, but the Tmux part of my terminal suppresses that. Actually, I might just, never mind. So, okay, 104, it seems to crash. So, or it doesn't, I'm saying that it doesn't crash at 104, but something is happening at 104. That is causing it to stop printing out our whole input. And so, now I still have the 3, 4, 5, 6. We give it a bit more, then we'll see that it crashes. I think this is around 110. So we now have know that there's a buffer on the stack. That buffer is roughly 100 bytes, probably 100 bytes. That number seems to make sense. There's maybe something behind it that's being written to, which causes our string to stop being printed because there's a null byte apparently. And there is clearly a buffer overflow happening because if we give it too much input, the program will crash. These are fairly important details that we are already learning just by giving it numbers of A's. So this is really part of the systematic approach that really helps to examine these kinds of programs, because you can really from very basic, just by being very careful and seeing, okay, when exactly does this stop behaving normally, you can already learn a lot of information. So the exercise, of course, already hinted you to start providing a %ps as well, and that is because this program clearly has a printf problem. We can use format string injection to start dumping parts of the memory. And you see here that the first few are printing some weird addresses. These are the contents of the first few registers, because remember, the calling convention says that the first few arguments that are passed through registers. So printf will look in registers for these first few arguments, and then only afterwards will it start reading memory. What we see after that is this 70, 25, 20, and we see that a whole bunch of times. Also, if we copy this again, oh, that was the wrong thing I wanted to drag on. Then you see that we see a whole bunch of those 75, 20, 20, 70, 25, 20 outputs. You see also that it appears that some of the register things have changed in value, but that's just, yeah, registers. There can be whatever stuff in there, so it probably left over by some other part of the program that did something. I'm not gonna care about those very much. However, you do see that this 70, 20, 25 stuff is happening a lot. So let me copy that and then open a web browser. decode. I like this convert string .com one because it's very resilient. Let me just take out all these 0x's, and then I press hex decode, and it says, let me enlarge that for you. Base the text you want to hex decode here. This one doesn't like it if you provide OX, so I've removed that. And you see here that there's all of these. We see a P, we see a %, we see a space, and then that again, and here's suddenly 2%. Well, why is that? That is because this is a little endian form. The bytes are written to the memory as part of the string. They are written to memory in a normal way, but what %p does is it interprets 8 bytes at a time, and it interprets those as a number, and numbers are stored in little endian form. So that means that this is all slightly garbled, because if it's 1 2 3 4 1 2 3 4 5 6 7 8, and then reversed, you'll see that this is exactly %p space, %p space, %p space. That is why this is in a weird order, but more importantly, we've learned that this means that we are seeing the input that we are giving to the program. Back to the terminal we go. Of course, I can also provide a bunch more of these guys, and then we'll see more. There are some interesting things going on here. We see here some other things. This looks like a address on the stack. Why is it an address on the stack? Well, it starts with 0x7FFFFF. This appears to be a address that is probably going to be a code address. So this is very likely a return address. Similarly, here there is another return address. Again, I see here that it starts with 0x55555555, so that's a return address. And here another one, 0x55555555, probably another return address. So if we go and draw a picture of what we now know from, we know that there is that obviously we are dumping the stack. There is at the top of the stack 7FFF. There are a function A and B, and these that's the stack frames that we are seeing part of terminal. We see here that there's some other function, some other stuff, then some other another return address, and then another return address, and that really suggests that we are seeing a bunch of different stack frames. So those are above us in the stack, and if we also know that we are probably somewhere here, and that there is some buffer, and we're going to assume that it's 100 bytes. And then here we have 0x555 blah blah blah, the address that we saw. And if we go back to the terminal, we saw that before that we see some other thing, this EC70 thing. That is probably going to be a frame pointer, because we know that before a return address there is a frame pointer, and that is probably going to be it. So we can also draw that one in. And it ends in 70. Before that, we see something else. which also appears to be some address on the stack. But the number of %ps that I've given the program still is within 100, I think. So let's try to make it a bit more. So you see that the formatting string, the OX70 2520, is overwriting everything in the memory. And we see that we have here a this address that we saw here before. That is very interesting, because everything behind it has been overwritten. We've completely blown over the stack. We've just yeeted all of those %ps all over the place. And completely crashed the program, because if you see that it doesn't continue anymore. But this thing has been written over our formatting string. So something has written there, and that also means that it has to be some other local variable within this stack frame, because the actual program, as in the normal operations of the program, it will write to locations that are legal, and it will not arbitrarily just overwrite part of a buffer. So this is probably another local variable, which means that this EBE0 variable, and now I will correctly switch screen, is probably here. EBE0. Nice, this drawing app also has a thinner line. This means that we've already learned quite a bit about what this stack thing looks like. We have a buffer. A buffer that's probably 100 bytes. Then we have not the greatest drawing app though. Some address, frame pointer, suspected, and the return address. This is already a lot of information that we learned. Sorry, I got distracted by the Google sound that my Google Home thing started making, and I didn't want it to start talking through my lecture. We have already quite a bit of an idea of what this function is now looking like, and we have not looked at any of the source code, and we've not had to, we don't even have access to debugger. This is all the information that we've been able to learn through printf. Excuse me, the coffee machine is turning off. Okay, sorry. It never knows how to when to shut up. And this sum address, we saw that it was not overwritten by the %ps because probably it was written after the %ps were read. What do I mean by that? Is that the location where this value is parked probably was overwritten by the OX70 string, the %p string, but then after that it was overwritten again by some other part of the program that came after the function that copied over all of these things over the stack. Fortunately, we have an idea of what that could have been. Namely, if we go to get_s, this is the manual page that we saw a bunch of times earlier in the slides with the deprecated, never use this, no check for buffer overrun is performed. What we see here is that it also returns a character pointer. And what is that thing? Get_s returns s on success, and s is the argument buffer that we gave it, a null on error, or when end of file occurs while no characters have been read. There are, of course, the usual caveats again, but that's not our problem. We are trying to break it anyway, so we don't care about get_s being a terrible idea. Kind of convenient for us right now. This is interesting. Get_s returns s on success and null on error, and that means that it's probably interesting to see, if you're writing a program, it's useful to check if your get_s has worked, because you might need to account for end of file. What this implies is that there is probably a local variable that contains a pointer to s, the buffer that is being read in. And that means that, going back to our picture, this could very well be that local variable, and that it points to the buffer that we are attacking. Let's try that hypothesis for now. However, we also now need to start worrying about making this exploit a little bit more reproducible. So let's go into attack.sh. I like to use %ps, and I want to start like that, and then we have a %p and a space. Very nice. I also want to add, if I specify a second argument, all of these arguments in shell scripts are just $1, $2, $3, and if it is not empty, then I want to add the return address at the string at the end. And I want to also use there the second argument. I need to put this within quotes, and then we end the if by typing phi. Don't ask me why. And then we can do nice things. Let me double check. Oh, excuse me. Yeah, reverse address is this function that we have here, and then we can give something, and then it will produce that in a little endian form. So going, this means that we can use attack.sh, and then we say we want you to do 30 of those, and we want to use the address that we thought, okay, this could very well be this pointer to the buffer, and let's see where it ends up. So we have here the input that we set up to give is now a 30% piece followed by this address. And we can try to see where that is going in memory. So we see here the %ps again, %p, and we see here that we see the address, and then there's this garbage attached to the end of it. What does that mean? Well, we have that we are printing this address and it's being followed by a space and by a percent. No, the percent is it's 25. It's followed by a space and by a P. That is because this has some small alignment thing going on. If I add, for example, another %p, you'll see that it starts to move up a bit more. You'll see that we now have that in this place, that used to be this null byte, we now have 0x7ffffff. And that the rest of the address that we have is now still in the previous part. So we are now between those two places. And that sort of makes what we're seeing here is that we are printing the memory 8 bytes at a time. So if you split everything into 8-byte blocks, we see that there are some bytes of the address in the first block and some bytes of the address in the second block. And everything, of course, what we want is to be nicely aligned. 32. What do we see? We have now got this thing in a nice place. And we see that that took 102 bytes. It's useful to keep track of that thing. But of course, we are still even before the original version of that place. But we can try to overwrite exactly itself and then it won't do anything. But I need to add 8 bytes. Which is slightly tricky if you do that with 2 bytes at a time. So, but I can add 18, 24. Yeah, if I add 8 more bytes, 8 more %Ps, then I should add 24 bytes, and we should see that it will end up, because then it's +8, +16, +24, that it ends up exactly here. We see that the program has crashed because instead of hanging, it has stopped. We also see that we have it in a nice place. No, we have it here. This is the version of the address that we wrote. This was the original place, and we see that in between we see that the frame pointer has been overwritten by the %Ps. But we also now know that 126 bytes is exactly how much bytes we need to write to overwrite this address. So that's an important number to keep track of. So if we go back to our, let me unlock my iPad, go back to the notes there. You know that we have 0 to 100 is the first 100 bytes that we write end up in the buffer, in the normal buffer. Then we saw that there are 4 bytes that we can write before anything happens. So 104 to 112 are the bytes that are occupied and will be overwritten again by the return of getS. Then we have the frame pointer, which is in the next 8 bytes. And then we see that in 120 until 126, we see that that's the location of the return address. And 128 actually, because they're of course 8 bytes long, but the top 2 bytes are null, so we cannot include those in the length of our string. So 126 is what it is. This brings us to the following. We now know how to get our desired return address in the correct place. We know how many bytes we need to write. So it's now jumping into the buffer that we have. And that's nice and all, but yeah, we're currently jumping into %p. And %p is not a executable program, of course. So we need to get our shellcode in place, because that's the code that we want to run. That's the functionality that we want to add to this dump program. So we can modify our attack script again. If I provide a third argument, then I need to add a space here. It's very finicky with that kind of thing. And I want to add the shellcode at the start. And we are going to start out with the variant that does bin ls, because shellcode, this program documents itself. We give it a type of shellcode that we want to run, and that can either be shell or that can be list. We can also give it a number of knobs that we want it to print, which helps us, for starters, pad the size that we are injecting, because that means that we can start to move things around in 1 byte increments. And it also allows us to, if we have a more vague idea of what the return address is, to have more of a margin to jump into. But yeah, we technically don't need any, because at this moment we have an exact understanding of where we think the buffer is going to be. But because I like the padding aspect of it, I'm going to also use this third argument to indicate the number of knobs that I want. If I then run attack with, well, I need to do something a little bit less. We want to use that same address again. I'm being an idiot, and I've not been showing you anything. Sorry. I've added here an if condition that does the if you give it a third argument, saying if $3, which is the third argument to our shell function, is empty and then not, then we add the shellcode in the list variant to the attack string at the start. And if we look at the shellcode thing, it has either a shell variant that executes bin sh, or the list variant that runs bin ls. And we can also check that by typing list. And if I give that to the hex dump program, xxd, we see that it started to run. This is the shellcode that we had in the slides, more or less. We can also see that if I give it another argument, it will start to prefix the shellcode with these knob bytes, which gives us that knob sled entry point into the program. And because I can really easily tune this, I can very nicely modify how long exactly this thing is going to be, which means that I can very precisely move around things, which is also a nice side effect of what we're doing here. It allows us to really easily control what we're doing. Back to the script. So yeah, that's what we do. This third argument we pass along to shellcode to use as the number of knobs, and we can now try to run that. So if let's see, use 30. Then we use the same return address again, and let's start out without any knobs. 129, okay, that is 6 bytes too many, so I can just reduce the number of %ps that we use. Ooh, that was already it. Excellent. We see here that we've obtained the directory listing of where this program is running. course, that's just the directory listing. You need to get what is inside this flag thing to complete the challenge. So what has happened? You see here that we have, again, correctly overwritten the return address. In our previous attempt, we know that we printed too many, it crashed, and we see here why it crashed, namely that the return address, the OX7F, has ended up behind where the return address is supposed to be. You see that we've overwritten the tail part, the last part of this address, with the top bits of the return address that we were trying to write. You see here that the return address where it was now also contains this garbage at the end, the 20, 70, 25 part. So that's why that did not work. You see that if we go to the variant down here, we see that we've correctly overwritten the return address, and that we will correctly jump into the shellcode, and that we didn't even need any NOP bytes. We didn't need any of the OX90's NOP instructions because we had this exact address. We knew exactly where we needed to go, which was very nice. If you don't know where exactly to go, I would suggest going back to the demo I did at the end of one of the lectures, where I used the frame pointer to compute and guesstimate an address. The nice thing here is that we have this directory listing, but that's just a directory listing. So what we need to do to finish up this attack is go back into attack.sh, switches over to the shell variant. However, who am I? This does not work. That is some situation that you might have been in yourself. And it makes sense why this is happening. But you need to know a little bit about how this type of program runs. So what's being run is it's doing echo attack string, and then doing netcut localhost 1327. The problem there is that this echo, this netcut, it reads input, right? That's of course how we are able to type things like this, and then it does something. It reads input. But when we just started like this, it reads input from something that we call standard in, the standard input, and it's currently attached to the terminal that we are operating. When you run it with a pipe, hello, to send the output of this echo command into this netcut command, what you do is you attach the standard input of this command to the standard output of this command. And as a result, neither this echo command its output does not appear here. Its output is being sent on to the netcut. Similarly, the input of this netcut command is being read from the output of echo. And what happens is that when echo is done, it has printed the line, and there's nothing for it that is left to do, so it ends itself. It will close its own output, which closes the input of the netcut. As a result, the netcut can no longer read anymore, and the input wasn't attached to the terminal anyway, so anything that I'm typing here is irrelevant. But there's a trick we can use. If I do this little bit of shell magic, I can concatenate these two, the outputs of these two programs, and then send them to NetCut. And what cut does, if you give it a space, a dash, is that it will read from standard input. I don't actually run the proper cut. This is usually what it looks like, but my nice versions also very clearly says I'm reading from standard input. And if I use that trick, you'll see that I can still enter input. And that is exactly what was going on at the end of this program, where it had this variant of the attack string, this version of this line that had the parentheses, the cut with the dash, the semicolon to keep open this standard input. And now if I run this, and I need to go a little bit back at what it was, 29. Not. Who am I? Apparently this server is a fan of Game of Thrones. The thing though is that we can also start seeing again what is here, and we now know what the flag is. So this means that we've completed this exercise. There was nothing else that we could do. You hopefully saw that if you work in a structured way and start to draw pictures like this with the information that you're seeing from, for example, such a stack dump, that you can learn a lot of info. Also try to, okay, if I'm seeing something that seems like something that you can't attribute, maybe hex decode it, try stuff like that to see if there's anything hidden there. The systematic working really helps, I would say, because it really gives you a clear understanding, okay, what's going on here. For example, if I would not have had this address, I could have used this information to use the frame pointer and then subtract 112 bytes and then use that to compute the start address, right? So this is a very helpful way of working. Just draw those pictures, keep your notes, and be very careful about what you do. We will also be publishing a write-up of this exercise soonish. I will do that after this lecture, and that write-up will mirror what we expect you to do in the exam. So what things we want to see from you? We want to really see your systematic way of working, how you apply the knowledge that you gain from the course, knowing that, okay, we have understand what a stack looks like, and that there's a frame pointer, and that if you ruin the frame pointer, the program will crash. Stuff like that we kind of want to see. Don't go into writing whole essays on the assignments, because I also need to grade it within a reasonable amount of time. And if you start spouting nonsense, of course, that's going to be a problem. But try to succinctly but accurately describe what you're seeing, and hopefully that will automatically also help you complete the exercises. Which brings me to Q&A before we go into the exam a little bit further. I will briefly open my email because someone sent me a bunch of questions, and then I've, in the stress starting up this online whiteboard, I broke some things. Okay. Someone sent me 4 questions, which seems like some good questions to start with, while you can post any questions that you want to ask in the chat. Okay. So this first question is, if you print a lot of %p, you would expect them to be at the start of the buffer being printed, but there's always some other values at the start before you see them appearing. Why is that, and what are those values? That is a good question. This is indeed, again, what we see if we run this attack, where we print, in this case, 13% Ps. We see only that they start here and not at the very start here. That, again, is, like I said, the calling convention. We see that the first few arguments are being passed on the stack, the first 6, in fact. And that means that we see 5 register values here. Why 5 and not 6, you may ask? Well, remember that also the attack string that is being passed to printf is an argument. So that is the first thing. The address of the format string that we are injecting is the first argument. And then we start to print all the registers behind that, and then we go up the stack. This is, again, the calling convention, and going through the slides of the lecture can be very helpful if you need to refresh your understanding of how printf tags work and how the stack works. The second question is, can we see the stack pointer somewhere, and can we do anything with it? Not easily. So if you have a debugger, of course, so if you can attach GDB to a program, you can very easily print the stack pointer, because you can just do anything. You can just print any register value, but that's if you are remotely, you cannot do that directly. The stack pointer is in a register, so that register value is not something that is easily accessible in the way that you could use a format string attack, for example, to print it, because you cannot address registers through a format string. It's not part of the stack. What you can find is frame pointers, and frame pointers are what the previous function's stack pointer was, more or less. So that gives you some idea of what the stack pointer was, at least at some point in time. What you might also see is that sometimes the stack pointer is temporarily put on the stack itself, but that is pretty rare, and yeah, probably at that point just looks like another address unless you know exactly what is going on. It is, but to come back to the question, can you see what the current value of the stack pointer is? Not directly, and not super accurately most of the time. Can you give some examples of how you would use the frame pointer during an attack, or what you would do with it? Why is it important? What you could do with the frame pointer, for example, is that during this attack, we used the fact that we had this information as the exact address. What we could also have done is use the frame pointer, and then I need to find a version where we don't overwrite it. Maybe here. The frame pointer as a proxy for that, because we could use that to compute this offset of where the buffer exactly was, subtract 110 from this address, then we would have ended up somewhere around this place, and then we could have used a bunch of knobs to enlarge the frame of the space where we could jump into, and then we could try to break it, get to the shellcode in that way. I think I've already demonstrated that type of attack during one of the lectures at the end. Another question that I've gotten is, are there other ways than buffer overflows to attack C and C++ programs? Yes. There are many other ways to do sorts of attacks, but it then often quickly becomes more complicated. An example of an attack that I did in the printf lectures was that I used the %n formatting character that can write something to demonstrate that you could also use that to change programs. There are more things that can go wrong, though. There's also, you know that if you write a program, then something that is a string and something that is an integer are two very different things. You cannot add 6 to a string. What does that mean? I didn't. Is weird. You may also have in Java some class, some object that is a car, and then you cannot add a summing up a car and a bicycle. What does that mean? And that is the idea of types. And that types, they say something about the data, and they define things like what operations are legal on them and stuff like that. There are no types once you've compiled a C program. This is something that only in C only exists at compile time, and once the compiler is done with it, it's just gone. And also, it's not very strict with them anyway, so it's very easily to confuse types, is the technical terms. And that is also a way that sometimes programs can be broken because they expect something to be in some format, but then it's not, and then they start to interpret it in a very strange way, and you can maybe use that. But that's all starts to get a lot more specific, a lot more in detail. You need to be a lot more careful about what kind of thing is going on, and you might also want to have source code if you're looking at that kind of attack. I am not seeing any more questions in the chat. Let me poke over to Discord. Yeah, okay. So with that, I think it's time to start opening up the exam stuff. I am logged in, great. Chrome. You see that there are a whole bunch new challenges that have appeared, and they've also appeared in an arbitrary order, which is great. Yeah, this was not the order in which I added them, nor the order of difficulty. So feel free to start with one and then another. That is completely fine. So there are 4 challenges. You need to complete them before the 3rd of July on 6 p.m. And they are, okay, something is still, wait. Okay, I've clearly made a mistake. These challenges, though, they will look much like what you had before. They are challenges where you need to hack into, or not necessarily hack into. You need to obtain a flag. And for example, in the guessing game challenge, there is a it's a game. It's the program takes a random number, and you need to guess that random number. Well, the problem is that random number is very big and very random, and there's no way you're going to guess it, so you need to outsmart it somehow. And if you guess the correct number, then you will obtain the flag, and then you can submit it, and you'll win that challenge. But don't forget that we want to see that write-up. So what did you try to start? What did you notice? What inputs did you try? how did you break the program? It's really show your work and try to do it in a sort of a neat and structured way, because that's easier for me to grade. And then you will get some points based on mainly the write-up. These challenges have also been customized for each and every one of you. That means that every student will get a different flag, but also that buffer sizes will be different between each one of you, and addresses will be different between each one of you. This is an important detail. So where previously the sizes of buffers probably more or less made sense, it was 100, 50, 200, 250. It will be anywhere between, well, I don't know exact numbers, but there will be odd numbers in there, because I've set up these challenges where relevant, not always relevant. If there's a buffer of input that it is reading, that buffer is a base size and then plus some amount. The base size because I need some space to work in to be able to do the attack, and then some amount just to make your life harder. So if you see that it's sometimes a little bit of a weird number, that is to be expected. The write-ups don't necessarily have a super fixed format, but kinda. And I will be publishing a write-up of the previous exercise as an example for what we would like to see you write during these challenges. I need to fix the bug that is keeping me from doing anything, seeing the actual things. And I will probably fix that within the few minutes after after closing this live stream. If there are no remaining questions, then I think I can end it with wishing you a lot of good luck with the remainder. It is hard to say how much time you'll need for each of these challenges. Again, you need to do them individually. That is very important. But it's a bit tough to say. This is typically the type of thing, these exercises where sometimes it goes very quickly, and you know and you don't make stupid mistakes, and then it goes very quickly. And sometimes you just mess some very small detail up, and then you keep trying, and then it's very messy, and then it sometimes takes a few hours. I don't think that it will really take a lot of hours, but you might need to invest a little bit of time, which is why I hope that I've given you ample time, and I would not advise you to wait until 5 p.m. on the 3rd of July to start doing these challenges. I will say that these two are related. Echo the Flag Part 1 and Echo the Flag Part 2 are, well, the Part 1, Part 2 probably already spoils that. This is a similar thing to what you did, and this was the guessing game one, and that I think is hopefully fun and not too difficult. You don't have to do any of this in one sitting. You can start something, work on it, and return to it later. Do note that the servers that you can start up using the Start Challenge button on the challenge page that I cannot show you right now because it's broken, it will be terminated. All the services will be terminated after they've been running for 12 hours. because I ran into some resource constraints. If you don't, that's completely fine. The challenges will not get re-randomized, they just get customized for you once. So if you start it again, you will get the same buffer size, etc. So it's completely fine to do something and then stop it, restart it, come back later or whatever. Just be aware that the port number that you will be getting will be different each time, because that's randomly taken from a pool of available port numbers, etc. I briefly checked my email and it doesn't seem like I've gotten any more questions through that channel either. So I think that we can end it here. I want to wish you very much luck. Please have fun, I guess. Don't be try to be a little bit ethical. Don't try to break the server once you've hacked into it again, because although I have some protections in place to prevent the worst of fork bombs, etc., it is still probably possible to degrade service, at least. That should probably be fairly easy and super annoying for me, because I need to restart things and then I get emails from Google Cloud saying I've used a lot of CPU time, and then but also for your fellow students, because that might mean that the service is unavailable for a little while. I also cannot postpone this deadline any minute. I need to have these things by 6 p.m. on the 3rd of July because I need to grade this within a very small amount of time. I need to have these results out to you within a week because they need to be available to you 9 days before the resit, and I need to start the resit. You need to have also enough time for that resit, and also the deadline for the resit is really hard and cannot be moved any later because of the way that the education center expects me to hand in the grades at the end. So don't bother trying to ask me for postponing. Please rather just start on time. I really hope that we give you as much time as possible. We've already moved this deadline back a little bit and really try to give you as the best chance that we can give you to do things. With that, I think this is a good time to end. The best of luck again. I'm looking forward to seeing your write-ups. I should probably end with a question though. At the end of a course, on the exam day, you will get an email from CNCZ with a questionnaire. You have seen that before, obviously, and that is the course survey that is part of the wrapping up of every single course. It will ask you the usual questions about the lectures, etc. Please fill in that survey, especially now, and not just for my course, but all of the surveys that you get. These surveys, they don't just appear into a black hole or into a cupboard somewhere. They really get looked at. They are completely anonymous, so don't worry about that, although that is not a good reason to use rude things, to be rude in them. Please be constructive and nice, but this feedback is really taken seriously. They are not only looked at by me or by the lecturer of another course. The feedback from those course surveys ends up in the course dossier. They often lead to direct points of action for improvements in later years, and they also get shared with the program committee, the opleidingscommissie in Dutch, which is an elected body of students and some staff members who really do proper look into all of these course surveys and really try to improve the quality of the education that you're getting. That being said, of course, this course survey is set up for normal times. So because we did things so much differently this year, I think I will be trying to send out another survey at some point during the coming weeks, where I will be asking you some questions along the lines of how did you like YouTube versus other things that other teachers tried. How was the CTF website? If you are a student who took this course in a previous year, how did you like it this year? There's hopefully not many of you, but those who are watching, I think they have a very unique insight into how this course went this year versus the last year. And I really hope that we can learn some things from what we tried this year round. Should the university be giving me a lot of money for an expensive microphone, or is the one that I've been using in my webcam so far good enough? These are some of the things that just are questions that are probably best answered to a separate survey. So I will probably be sending that out to you. And you would really help me if you fill that in, and not just me, but probably also these results will be. I will share if I send out such a survey. I will make sure that it is anonymous, and that I will share the results of that with the program committee, so that it gets goes into the proper channels, and then we can hopefully learn something from it. That is it for me. Thanks for taking this course and joining me on this journey through the depths of the ugliness of C. For you, the journey is not done, but hopefully it will be soon and satisfactorily. I hope that these challenges will stimulate you in the right ways, that you have some fun with them, and it's a little bit more interesting than just writing an exam and just cramming as we used to have. And yeah, it's this was it for Hacking a C in this year, and hopefully I won't see you again in 2021's Hacking in C, but maybe in some other course down the line. Good luck with the exam.